Okay, what I want to show you is a little bit of an algorithm to help you determine which analysis you should do. So we talked a little bit about descriptive summaries in our last class. We know there's 4 types of data. Dr. Fleischer is going to talk more about categorical and ordinal data in class, and I'm going to focus on numeric or scale data. So one of the big advantages of graphing out your data is that you see logical or illogical trends. This helps you identify outliers. It also helps you understand and interpret your statistics. And the way I try to explain this to students is if you look at your data and you see what your data is doing, does it make sense? Are you seeing what you expect to see? And then statistics confirms that there is or is not a true difference. But often in graphing or making a table of your data, you can actually see what's going on and help you. The statistics just helps you confirm that. So that's where scatter plots for regression, box plots for differences are really helpful. So this is a statistical decision tree. We're going to talk about relationships down the road. So I'm going to focus today basically on differences. So contemplating basically the information related to this information here around differences. So we have both categorical and quantitative data. Dr. Fleischer is going to talk a little bit more about categorical, and then the type of question. And we're going to go into both, but for this component, we're only going to talk about differences. And so depending on the number of groups, if you have 2 or more groups, then you're going to have different terminologies. So I'm going to start you with the simple. So we're going to look for differences. Sorry, I forgot to change that. Differences between samples. So are the 2 groups independent of each other? So I have healthy and injured. Those are 2 groups. Or are they dependent on each other, which would be a pre-post design? So if they're dependent on each other, the baseline score and their follow-up score might be related. If they're a related or paired sample t-test and they meet the parametric assumptions, then you're probably going to do a paired t-test. If they don't, then the non-parametric analysis would be a Wilcoxon sign rank test. If they're independent, so if I have 2 groups and I want to compare them at baseline, say the healthy versus the injured in the sample that we're discussing, then I would say I can use an independent or a 2-sample t-test. If they're non-parametric, then that would be a Mann-Whitney. So if you have more than 2 groups, or you have more than 2 time points and measurements, you might have to look at a more repeated type of analysis. So if they're dependent, so you're going to measure the same group 4 or 5 times, and they meet the they meet the assumptions, then you could run a repeated measures analysis of variance. If they don't, there's a non-parametric component, which is called a Friedman's. And I'm going to run a repeated measures for you in demonstration number 2 or number 3 as we go through this video. If there are multiple groups, so you have a number of independent variables, so you might have 3 groups. You might be able to do a one-way analysis of variance. The non-parametric of that is a Kruskal-Wallis, or you might have multiple variables, independent variables, and you might have to do a factorial ANOVA. Now, I'm not going to be able to do all of those analyses, but I'm hopefully introducing you to some basic components of that. So some people think better with a matrix, some people think better with an algorithm. So basically this is sort of the same bit of data, just presented a little differently. So if you're comparing the average of 2 groups and you're using numeric data, then that's going to be an independent data. A non-parametric version of that would be a Mann-Whitney or a Wilcoxon sign rank, depending if they are related or not related. Remember, that the Mann-Whitney is independent. The Wilcoxon sign rank is for related or dependent variables. If you have 3 or more groups, then you're looking at a one-way or a Kruskal-Wallis. If you're looking for differences between matched pairs, so you might have, again, numeric data or scaled data, your time across time, so at 2 different time points or multiple, 2 different time points, you're looking at a paired t-test and a Wilcoxon sign ranked. If you have 3 groups or 3 measurement times, you're looking at a repeated measures for a parametric or normally distributed, and a Friedman's test for non-parametric. So that just sort of organizes our thought process of which test to use. There's a lot of information out there. So I'm going to get out of the PowerPoint, hopefully, and I'm going to go back to our assignment. And so we have multiple steps here as we go through this research question. So I'm just going to take them one at a time. So the first hypothesis that we're going to address is the simple analysis of one muscle group. And so we're going to ask the question, is that in the injured group, do they get stronger after the intervention than the healthy group? So in class, I'm going to use the upper trapezius, and so that's the example. And I'm going to do it 3 different ways. I'm going to do a paired t-test, then I'm going to do the non-parametric equivalent of a Wilcoxon sign ranked, and then ultimately a repeated measure ANOVA with 2 factors, because we have 2 groups at 2 time points. I might be violating some assumptions of normality, but just to demonstrate this. And then at home, you're going to decide whether it's appropriate to either do a parametric or a non-parametric analysis for the average of the posterior deltoid and lower trap. So you'll have to run the analysis of normality, do a Shapiro-Wilk test, and then make a decision of which analysis is appropriate to do and run that analysis. So you'll copy that data analysis from your SPSS into Excel, label it clearly, and then interpret your findings of your analysis. So just write up a couple of sentences, real short, on the Excel to explain the findings of that. And as you want to, you can use descriptive data to help you interpret the results, which sometimes makes it a little easier to do both the descriptive data and the significance as it makes some sense. So how would we go about doing that? So we're going to do a paired t-test. So because they're paired t-tests, we're going to look at the pre-scores to their post-scores by each group. So we're going to have the healthy group, and then we're going to have the injured group. And we want to see, did we see more increase in strength in the injured group than we did in the healthy group? So we're going to go to our SPSS data. And again, I'm going to split the file between my groups. Oh, sorry. Did I not hit the right one? There we go, sorry. Organize output by groups. We're going to use groups. I go back and I look at the data. You're going to see all my group 2s and all my group 3s. All my healthies are together, all my injured are together. Okay, so now I'm going to run a paired t-test. So I'm going to go down here and I'm going to do a paired sample t-test. Now for this example, I'm going to use 2 variables. Ooh. See if I can spread this guy out, make him a little bigger. We're going to do the upper trapezius. So we're going to take the pre-upper trapezius average strength and compare it to the post-upper trapezius strength. So I'm going to go down into my labels, And we're going to use the average of the two efforts. Here's my that's lower trapezius. Here's 1 and 2. I'm going to use my upper trapezius baseline strength. Obviously, I'm skipping the step of testing for normality, which I don't want you to do, just to make this move along. And then here is the post upper trapezius strength. Okay, so now I'm going to have it split out the results. I'll have a healthy and I'll have an injured result to see if there was a significant change in strength in both or in one group. I can ask for some options. I have all my data there, so I should be good. I'm not doing a bootstrapping technique, so simply hit OK. And there's my healthy group. It gives me my means, my standard deviations, the number in the group, so I can use this for my descriptive data. This is showing how great the correlation is between the healthy group. It's pretty high. That's typical. 0.6, 0.7 is really common. And then this is the interpretation of the data. So pre-upper trap to post-upper trap, there was minimal change. This is the mean change. The paired differences, quite a bit of variation. And then here's the confidence interval of the differences. This is my t-score, my degrees of freedom, n-1, I had 14, and as you can see, 0.958. So nowhere really close to being significant. In my healthy group, 21 versus 21, big surprise, right? Not really an exciting change. So let's see what happened in our injured group. Let's go through this analysis again. I go from 14 to 20. There's only 9 in this group. This is our standard deviations. Correlation a little lower, not horribly different. Scroll on down here. And down here, now we have a 5-point difference, which makes sense. Their strength got stronger post-changing by 5 points. So it would seem that that was a increase in strength. Was it significant? So now I go over here to my t-score. My degrees of freedom is n-1. And sure enough, I see a significant increase in upper trapezius strength following the exercise program of this prone horizontal abduction exercise. So what I'm looking for you to do is to interpret that information from my results. So you can make a table, you can copy and paste this stuff over. I think what would probably be the most efficient way to do it would be to take the descriptive data, copy that, this is my healthy group. It says it here too. And then my analysis of variance for that. I'm sorry, my paired t-test. Jumping ahead of myself. Alright, so there's my paired t-test with no significant difference right there. Now I'm going to have my injured group. And I'm going to do the exact same thing. Spss, there we go. Copy, paste, and my significant difference. Copy. Paste. All right, so what I asked you to do is you can build that table or leave it like that. I'm not too worried about that, but I want you to interpret this. So I asked you in the instructions for your homework, once you decide which analysis, part B is to interpret your findings. So what I would want you to do is write up a short results section on the Excel page. So on that Excel page, you can go back and you could write your interpretation of your findings. And it would be something to the effect that no significant increase in strength was observed in the healthy group following exercise program. And then a lot of times what I see people do is they'll write means and standard deviations. That's fine. Or you could simply refer them to a table. Since you have the data above, you could label C healthy data, or you could say C table 1. That's up to you. But what often is not said clearly is that people try to interpret the p-value. And if you simply just write the sentence, there's no significant difference, and then state the p-value at the end, it sort of just functions almost like a reference to the statement you just made. Just like when you're writing a literature review, you might reference somebody who's doing it, and then you put a citation at the end. So no significant increase in the treatment in the healthy group following the exercise program, and then I could simply go p equal to 0. I think it was 98, is that right? 96. 96. And then the other interpretation is following the exercise intervention, the injured group demonstrated a significant increase of 5.8 pounds of force. And again, this would be P equals 0.008. It's best, if you can, to go on and write what the p-value actually equals. That makes it make sense to the reviewer, as opposed to greater than or less than 0.05. If you have to do less than 0.001, that's fine. That's an interpretation that's used. And so that's a statement of my results in written form. And if you wanted to add an interpretation of that, which we often do in the discussion and the conclusion, that would be fine. But I typically leave it relatively straightforward in the results section. But that's what I'm looking for on this. I hope that helps you understand what I'm looking for on paired t-test.